喂，一二三。喂。
所以因看难看些。
很开了。
无一定看到。
敢若
看到我呢？哦，安尼我得。
你谁落音？
我是咩？我是啊，你得比这电影先啊。OK。啊，最后要开始啊？啊，已经开始啊。已经开始啊。哦，所以哦，不是后别讲话呢吼。哦。讲笑的。讲笑的名字。对，哦，法都无，哦，无犯法嘛。OK。安尼，啊，我即摆在创，我着加一年，吼，就看会对 ，OK。恁大家都迄个啊，即个我会做到啦，吼，迄个算家伙 ，OK， 吼，你啥物名 ？What's your name? What's your name? 苏荣银，哦，啊，你啥物名？
刘一珍。
哦 ，OK， 啊，咱哦，你大家拢熟悉。
陈之颖。
我变迄个 ，OK，movie star，OK，
郑宇选
，OK，TV star，OK。
张成泰。
林嘉阳。
姚义安。
刘成荣。
爱行吼，啊，恁大家拢变迄个 TV star，OK。
郑芳怡。林小军。
啊，你较慢讲呢。
李玉宽。
哦 ，OK。好，啊，你讲过啊？你自我介绍过啊？哦 ，OK。
梁彦章。
哦 ，OK。
许修伟。我叫自己。
OK，good。
黄木群。
黄木群哈 ，OK。我讲过了。OK。
吕建宇。
OK。哎，哦啊，这个上重要的，这个迄个，哦，那个解中音啊 ，OK，yeah。
老师好，我叫施小柔。
OK，good。对。哦，多谢你。
我叫曾昭成。
OK， 好，安尼，好，安尼，我不用这袂要紧嘛。哦，对，我不用这袂要紧嘛，哈。OK， 好。我安尼真好啊。Yeah，OK。所以 ，OK。Pointer，OK。咱讲到底，遮晓，咱总讲遮晓，要袂啦？哦，叫他稍微。哦 ，OK。哦，咱你袂讲到遮嘛？哈，还没有嘛 ？OK。哦，遮啦哈，遮，是不是？啊，到遮了哈。OK， so OK，let's use English。OK， 开玩笑当然啦哈。国语那会使啦。OK， so yesterday we， 今晚偌济人？5个，加一个。OK，that's good。Yeah。Okay, so yesterday we derived the kind of discussed, not derived. This is called perturbation form of the equations because it's not linear. Okay, because this is nonlinear term, right? Nonlinear term, and this term can be ignored if we consider small amplitude. That means linear. Okay, so then we can ignore that. Okay, and so if we ignore this. So let's probably do it term by term. Okay. So 3.44. Okay. So now if we assume, okay, U. Okay. So if we assume, okay, if we assume U prime is much less than capital U, V prime much less than V. Okay. And that's linear, okay. And then we also assume 2D, okay. That means 3.44. The first term will remain same, and then second term will become U, partial x, right? And then 2D. Okay, our 2D is on X and Z plane. That means partial y will be equal to 0. Okay. In y direction, there's no change. Okay, no variation. So we can ignore this whole term. Okay, and then the last one will become same. Okay, the h prime dx equals to 0. Okay, and then second equation 3.4.5 will become partial v prime partial t plus u partial v prime partial x. Okay, and then third term will disappear because there's no variation in y direction. The y 方向没有 okay 没有变动 so okay partial v prime partial y equals 0. Okay, so the whole term is gone, and this term is gone too. Okay, so become 0. Okay, and 3.4.6. Okay, you see, we also assume flat terrain, no bottom topography. Okay, okay, bottom is flat, so that means h sub s terms are gone. Right hand side becomes 0, and this term is 0. Okay, and this is gone. So we have the u prime dt plus u partial u prime partial x. Okay, and this term is gone because there's no y variation. No y variation. That means partial y equals 0. Right. Okay, and then let me know if you don't follow me. Okay. Okay. Number one. Okay. If you want me to use Mandarin or Taiwanese to explain, okay, you say this. Okay. You say Doctrine number one. Okay. And then this is gone. And then here we keep h and h prime. Okay. Because h prime term will be nonlinear, so only keep h terms. Okay. So h plus h prime, hs, okay, partial u, partial x, plus partial v, partial y. Okay, this is gone, right? Because 2D. Because 2D. Okay, so partial y, no matter which equation, which variable is equals to 0. Okay, and it's 0. Okay. Hmm?
3.4.6 is partially
Which one? First term? H prime. Oh, yeah. Thanks. This one?
No.
Oh, yeah. Partial H. Yeah, okay. Yeah. That's good. That means people are listening. Okay. Not sleeping, right? Okay, and then so then this will become H plus H prime times du prime dx, right? So this term, I'm talking about this term. I'm talking about this last term on the left-hand side, this term. So become like this. But this is gone because linear. Because it's non-linear term. Okay. So then the last one becomes simple, very simple. This term become partial h prime, partial x, right? And then equals to 0. So the three equations reduce to this if it's two-dimensional. Okay, it's two-dimensional. Let me go down a little bit. Okay, if it's 2D, linear means small perturbation. So your perturbation could not be very large. Okay, that means U prime would be much less than basic wind. Okay, V prime also less than basic wind in y direction. Okay, 2D means partial y equals 0. Okay, so reduce to y moment, x momentum should be reduce this, and then this last equation become like this. Okay. Yeah. Partial. Oh, U prime. U prime. Okay, that's good. Okay, so this is U prime. Okay, like this. Okay, so we can erase this. So you may wonder, where does this go? Okay, where does this go? Okay, so this one actually is the V prime dt equals to 0, right? And ddt for two-dimensional will be just partial t plus u partial x, right? Okay, agree? Okay, so this is in simple way to look at is like in calculus. Okay, normally people write this way, ddt of v prime equals to 0. Okay, and so this means v prime will be equals to 0 to certain time of v. Let me see. Integration. Okay, so we integrate dt of dt right. You can integrate this. We multiply dt here. Okay, and this is 0, right? This is 0, right? This is 0 times. Okay, so this is 0, right? This is 0 times dt. Okay, so this become like this. So this become t and dv prime, and this becomes v prime. Okay. Okay. So sorry, this becomes v prime at t minus v prime at 0. Right? Because the v prime equals to v prime. Okay. So if this is 0 to t, this means from 0 to t. That means v prime at time t minus v prime at time 0. Initial velocity. Okay, so this becomes, this equation 3.4.5 becomes dv t equals to v prime at 0. Okay, so initially, if you don't have y wind, then there's no y wind. If initially you have v wind, then that wind will keep same direction, so it doesn't affect our solution. Okay. But if you have rotation, that's different story. Okay. Like, so say here is ocean, and here's land. Okay. So your system could be like 2D, but okay, you can calculate v prime. Okay, for that problem, like so, like this, like when you in the morning, and then we develop the sea breeze coming in. Okay, and then if you have rotation, if this is just 2D, no rotation, it just keep coming in like this. So then everything will be identical in y direction. This is y direction. Okay, this is y direction. Okay, everything identical. Okay, but if you have rotation, then you start to have reflection. deflection to the right. Okay, so then the wind will be in the beginning, wind this way, eventually, okay, and then eventually become like this, Okay, you understand what I'm talking about? Okay. Let me try the Mandarin, okay? Just没有 rotation, okay, and then initially there's no V wind, then okay. So if initially have V wind, then that V wind at that time will keep same. Okay, 所以假设没有 Y wind， 那 okay as time goes, V wind still same thing, so you don't have to worry about it. You understand? Okay, that's what this means. Okay, so basically you still have 3 equations. Okay, so now we just write down 2 equations because there's no concern to us. Okay, no change with time. Okay, once you have it, or normally you consider non-zero, then it will be V prime also 0. But if initially you do have V wind, like in sea breeze, initially it's kind of blowing, 像 sea breeze 怎么讲？哈，海风，有 sure？ 海风 ，OK 我伫阮兜放鸟哦，一天到晚吹海风 ，OK， 海风 ，OK， 所以海风 ，OK， 海风这样吹过来，对不对？吹过来呢，如果有 rotation， 它就慢慢转成变成这样，到最后呢，变成 geostrophic balance。So then we'll keep doing this way. So you can still have V wind because here you have this U wind, and you have this V wind here. Okay, so you can have V wind, but V wind will be same everywhere, so it doesn't matter. So normally we ignore that one, that equation. Okay, basically you still have 3 equations, but we can just use these 2 equations, and then you can combine them into this one. Okay, into the 3.4.9. Okay, how many people have done this before? How many have this done before? Yeah. Okay, probably in which course? Oh, that's good. Okay, that's good. So you can, okay, combine them together, right? And how many have you derived this equation into that? Okay, from these two, 3.4.7 prime and 3.48 prime to 3.4.9 prime. Have you? How many? No? Maybe we should put that into homework. Yeah. It's pretty easy, right? Okay, so I'm not going to go through it because that will take too much time. Maybe that you do it, okay, at home. Okay, so now you combine into this equation. Okay, and this equation is okay, have a general solution like this. Okay, like this. If you don't believe, and f is any function. If you don't believe it, you should substitute this into there to see it works or not. Okay. Okay, so I guess I'm not going to do it. Okay, it's pretty simple and also take too much time. Okay, now assuming we have bottom topography. Okay. No, sorry, initial disturbance. So this f is any function. So assuming initially we have this perturbation. Okay, h naught and the p square divided by x square plus b square. Now this. So say if we have the shallow water like this, and this is capital H. So this depth. Okay, and this is only one layer. Okay, and so initially, if we have disturbance like this, okay, like this, and this is called the pear-shaped function, pear-shaped. Okay, pear-shaped function. Okay, so you have this. Then the solution will be f of this. F now is this function. So then it will become, okay, h naught divided by 2 h squared. Let me see. This is supposed to be b squared. Okay, so b squared. Supposed to be b squared. Okay, so b squared. Okay, and then become this x plus u minus square root gh. Okay, t divided. Okay, so you can derive that easily. Okay, as I said. Okay, any questions so far? Okay, that's good. Okay, so now and change this to be b squared. Okay, to be b squared here. Okay, yeah. So I'm not going to repeat that. I think that's kind of basic dynamics. And you don't understand, probably can come to ask me, or okay, I can show you, but for now we don't have enough time. Okay, so now if we consider we have a bottom topography. Okay, so basically what 3.4.14 okay says is this wave, okay, in the middle is going to break up into half of the amplitude and then propagate one rightward, one leftward. Okay, so this one will eventually break up into two, like this, and one propagate to the right, one propagate to the left. Okay, and this will be h naught. This will be h naught divided by 2. Okay, that's what this means. Okay, that's this means. Okay, divided by this. Okay, so I'm not going to spend too much time on that. My focus will be on the mountains. So right now, let's look at, if say we have kind of with okay, obstacle. So at the bottom, we have h sub s. Okay, then we are going to have additional term here. Additional term here. Okay. And now next thing is we are going to make one more assumption. We assume it's a steady state. Okay, steady state means no change with time. Okay, that means partial t will be equal to 0. Okay, no matter which variable. So now, if partial t equals 0, then what happened? This will be 0, right? Okay, so let me write down there. Okay, so we consider 3.4.16. And now we assume steady state. Okay, steady state. 按照讲，啊？稳态度，稳态流。Okay, 稳态流. Is that you don't know? You forgot. Okay. Okay. So 3.316. Okay. For okay, assuming steady state. Steady state 稳态流. Okay. Steady state flow. Okay. Steady flow 稳态流. Okay. So 稳态. Okay. 稳态. Okay. So then that means partial t equals to 0. So then this will become u partial u square, and then h prime. Right, the first term. Right. Everybody follows me? Yeah? Okay, and then second term, we still have GH, and then partial square H prime partial X square. Okay, and then this term, okay, is mountain, right? Mountain normally doesn't fluctuate with time, so it's kind of steady state. But this kind of problem actually can apply to flow over a sand dune. Okay, sand dune is satchel. Okay, because satchel bottom topography can change. Okay, so you can actually apply zero water equation to do satchel problem. Okay, but right now our mountain is fixed, so there's no for this term. Okay, so then it becomes U square, right? And then partial X, and then partial H sub X, partial X. Okay, so this actually becomes U square partial H sub S partial X square. Okay. So in other words, we have the square H square dx square minus GH the square H square dx square. Okay. And then the square dH dx square. Okay. And one rough way to simplify this equation is because we have partial X square, second derivative, so we just delete it, okay, remove it. Okay, that's rough way. But rigorously speaking, you cannot do that. Okay, you cannot say, oh, every term has partial square, partial X square, then you just remove it. You cannot simply do that. Okay, you cannot say, oh, because we have this. So then we have U square, okay, H prime minus GH, and H prime equals to U square H sub S. Okay, you cannot do that. Okay, a lot of people do that. Okay, but theoretically you cannot do that. Okay, so what you do is you take integration. Okay. Assume or maybe assume far away negative infinity. Okay, negative infinity far away. So this is mountain. Okay, this is basic flow. Far away here. Far here is x equals to negative infinity. Okay, and then you negative infinity to x. Okay. And then GH is square H prime dx square equals to negative infinity to x, and U square the square H sub S dx square dx, yeah, dx here. Okay, so you have this square here. Okay, so then U square you can pull out, so it becomes U square and then negative infinity, okay, like this. So then integral of, I'm talking about this term, square H prime dx square dx, that's equals to ddx, okay, of the H prime dx. Right, agree. And then this cancel out. Okay, this become the H prime dx, negative infinity to x, negative infinity to x, negative infinity to x. Okay, so this becomes like this. Okay, and then let me see. This means the H prime x dx, and then minus at x, okay, minus the H prime dx at x equals to negative infinity, x equals to just x here, and x equals to negative infinity, okay, like that. So if you assume at far infinity there's no terrain, then this term will be gone. Okay, so then this will reduce to the H prime dx. Okay, the first term. Okay, you do same thing here. Okay, that would be the h prime dx, and then equals to u squared the hs dx. Okay, and you do one more time. One more time. So the key point here is you have to assume for doing this, you cannot simply say every term has the partial derivative of x, partial square and partial x square, and then you just delete them. You cannot do it. You theoretically you're supposed to be do like this, and then you have to do assumption. One assumption is for infinity, there's no disturbance. H prime is 0. Okay, so you have to do that. So anyway, so okay, you do one more time, then one more time, then this will become u squared h prime minus gh and then h prime equals to u squared h sub s. Like this. Agree? Yeah, understand me? Okay. Okay, so now reduce this, and this one can be combined together because left hand side we can combine to be u squared minus gh and then h prime equals to u squared of h sub s. Can you see me? Okay, yeah. Let me know if okay. Sometimes I forgot because when I was younger, probably younger than you, when I was younger than you, I went to a teacher's college, junior teacher's college, Sichuan. Okay, okay, and Sichuan, all I learned is gone. Okay, only thing I remember is, okay, when你教书的时候，你要 motivate 学生 ，OK， 要引起动机 ，OK， 好，这是为什么我一直讲笑话 ，OK， 一直讲笑话，开北杜姑 ，OK， second thing I remember is， 你在教书的时候哈，不可以看3板，不可以看天花板、地板，还有什么白板。以前是黑板 ，OK， 所以不可以看3板 ，OK。Yeah, so sometimes I do this. I have to be careful because people cannot see it. Okay, so I have to stay aside. Okay, but sometimes I forgot. Anyway, so it becomes this. This is the final equation like this. Okay. Yeah. Right. Positive. Which one? Which one? This one? Yeah. If you are kind of considering easterly flow, yeah, you can do that. Okay. Yeah. But normally you don't do that, right? Because x direction is to the right. Okay. But you can do that. But you have to.
But we can get the same result.
You can same result. You just have to be careful because you become negative. Okay. Your capital U is negative. Okay. I can erase, right? How many people are there? Huh? Still 4. Okay. We should get them an award. Okay, so they stick with us. They are probably students, I guess. Steady state, yeah, students, yeah. Steady state group. Okay, that's good. Yeah. Okay, so become like this. Okay, and then H prime is the perturbation height. Okay, to the water depth, capital H. Okay, so this means we have H prime equals to U squared. U squared is greater than GH. okay, or u greater than square root gh. Right? Then this will be positive. This will be positive. Okay. Then if other situation is, sometimes it happens if u square less than gh or u less than square root gh. Okay. Then this will become negative. Okay. So h prime will be proportional negative h sub s. Okay. Yeah, I think we should take a break. Okay. And we'll continue after the break. 10 minutes break. Okay. Yeah. Okay, thank you for listening. We are going to take a 10-minute break. Okay.哦，这个哟，我无电池。哇，咱拄啊走来走去，因都管袂着。咱这个走一遍。 Okay, so chào. Chào làm cái gì vậy? Oh, okay. Okay, so if U square is greater than GH, then basically what we have is, so these have two cases. Okay, then where H just simply equals to U square over U square mass GH times H sub S. Okay, if for the second case, then H prime will be equals to U square minus GH minus U square. Okay, and then in the beginning it will be negative, right? So this term inside bracket will be positive because GH is greater than U square. Okay, so like this. So there are two cases. Okay, yeah, and well, some of you probably are familiar with this. Okay, let me just do it something quick. Like if we divide by U square on the right hand side. Okay, so then here this term, then this can be maybe this is a very simple thing. Okay, so this implies prime equals to 1 over U square 1 minus square root GH over U square. Okay, so okay. Okay, so there are different ways you can do it. I just try to find a simple way for you to understand it. So this H prime equals to, if I divide by GH, okay, then it will be U square divided by GH, and then it will be U square divided by GH minus 1. Okay, H sub S. Okay, so now if we define okay, a number, okay, equals to U square over GH. That means F will be equals to U divided by square root GH. Right. So then this will become what? This term will become F square, right? Divided by F square minus 1 H sub S. Or we can write as 1 divided by, okay, 1 minus 1 over F square H sub S. Okay, and this is called the four number. Four number, how do you say in furusu? Okay, furusu. Four number, okay, yeah, like this. So this means, okay, this means if U greater than GH, that means U over square root GH will be greater than 1. Right? Okay, right. And that means full number is greater than 1. This means full number is less than 1. Okay. So for short, if full number is greater than 1, then we have H prime equals to, okay, this H prime equals to U square over U square GH. Let me don't repeat, okay, this is simple, just simply proportion to H sub S, because this is positive, okay. F greater than 1, Okay, yeah, greater than 1. Yeah, greater than 1. If for number where these two cases less than 1, h prime less than proportional to negative h sub s. Okay, so those details I just kind of ignore it now. Okay, so this means what? This means you have disturbance, okay, for steady state, long-term disturbance becomes steady state. Then if I have a mountain here, okay, and this is h sub s, okay, that's mountain h sub s, okay, like this. Then the perturbation here will be proportional to this. So when it goes up, okay, so it goes up like this. Not necessary to be same height, but will be proportional like that. So when you're mountain, okay, you go up. That makes sense, right? Okay, so if I have a mountain here, topography here, flow comes in, okay, flow comes in, let me see, depth, flow comes in, will go up and then go down, okay. One thing strange is, so this is f greater than 1, okay. But when f is less than 1, the problem is this goes down. Okay, because this is h prime. Okay, this h prime is less than 0. Let's go down. Okay, because h prime is proportional to negative h sub s. So if we have mountain here, bottom topography here, this will become negative. Okay, so that is difficult to understand, right? Because flow comes in, and then when your mountain is supposed to go up, but it goes down. Okay, so we're going to explain this quickly. Okay, so here, basically what we have is h prime equals to h sub s divided by 1 over 1 minus f to the negative 2. Okay, and f is defined as this. Okay, f is defined as u over square root gh. Okay. Okay, so this is a solution. Yes, solution. Okay, now we wanted to find out what's the physical meaning of this. Okay. Okay, so f greater than 1, we have h proportional to mountain. So when you have mountain, okay, the perturbation will be just proportional to the mountain, not same height, but at least proportional. But when h is less than, f is less than 1, then it's going to dip down, passing over the mountain. Okay, so that's curious, right? That's kind of strange. Okay, so here I just make a kind of comment here is maybe we can come back here, okay? Because it is right now, I just try to make sure you understand the dynamics here. Okay, so this we're going to talk about that later on. Okay. Okay, so here. Look at these two, okay, cases. Okay, these two cases. Okay, they're kind of steady state cases. Okay, and so here, what happened is your flow comes in with basic flow U. So then you have a kinetic energy is equals to 1/2 or times U. Okay, and basically, actually, it's probably supposed to be 1 over f rho times u squared. Okay, that's the kinetic energy. So you have kinetic energy here, and when f is greater than 1, that means u, f equals u greater than square root gh. That means u is large. The basic wind is very strong, and that means it's strong, have large kinetic energy. And that kinetic energy will be able to, okay, help the flow to going over. But when you're going over, because your elevation is, okay, your kind of height is kind of elevated, That means you have to convert some energy, kinetic energy, to potential energy. Okay, so just like, okay, if a clamping stand up here, you have to, okay, you have to kind of increase the potential energy. Okay, so part of the energy coming from the kinetic energy. Okay, so then, but since basic flow has enough energy to, okay, clamping over become part. You still have the kinetic energy, but part of the energy become potential energy, and then coming down, you convert back to kinetic energy. Okay, so that makes sense. Okay, so now how do you explain when you have dip down? It's because when it comes in, your U is not strong enough. Okay, so you don't have enough kinetic energy to climb over the mountain. So what's going to happen? Okay, so when I come here, okay, so I try to come here. Here's bottom topography. Okay, so say I'm flow, okay, particle, come to here. I try to go over it, but I just don't have enough energy. Okay, okay, okay. So what do? I go down, right? I go down, and then I go down to go over, jump over. Okay, it's because you have to accumulate, convert your potential energy, okay, to convert part of it to become kinetic energy to go over. Okay, so then I try to go over. I have to go down and jump over. Okay, and that is okay. You kind of try to use part of your potential energy. You go down, right? Potential energy. Okay, 位能 ，OK， 降低位能 ，OK， 转换成动能 ，OK，go over. So then you dip down. That's why you go like this. And these two are the cases we say there. Okay, and here we have different cases, 3 or more cases, and they are kind of time dependent. So that their solution is not here. Why? When I solve this problem, very simple, right? Just algebra, no calculus. But when I solve it, this solution, do you feel like there's something there we don't really solve it? Okay. Is when this is equal to 0, you have no solution. Okay. We just assume it's not 0. One is positive, one is negative. Okay. So when it's 0, what happened? Okay. When 0 is called critical state. Critical state. It is 0, a critical state. So when you're critical state, you don't have steady state solution. So what's the solution cause? It's because it's time dependent. Okay. So flow is kind of transitional. Okay. Flow is kind of changing. Okay, with time. And so it's not in our steady state solution. Okay. So here that means no steady state solution. Okay, no steady solution. That's why you don't see it. You cannot solve it because it's 0. Okay, in the denominator. Okay, formula. Okay, formula is 0. You cannot solve it. And why? It's because it's not a steady state. And then you have 3 possibilities. One is this kinetic energy, become potential energy, but then part of it become of kinetic energy, and then you have disturbance. There are two waves. One propagate downstream, one propagate upstream. Okay, so remember we talk about that we have this disturbance, and then part of it you have this one, you have this one. One is propagating downstream, one is propagating to upstream, and this one will go slower because you have basic flow coming in, so this goes slower, and this is called upstream propagating wave. And this one downstream propagating wave. And this one can develop into hydraulic jump, a jump, come down, because it was down, the downstream, okay, down slope, and then, okay, sorry. Mountain is here, mountain is here. So this one will develop, okay, this one will develop into hydraulic jump like this. This is called downstream propagation jump. This is called upstream propagation jump. Okay. And this jump is propagating. This jump is stationary. Okay, stationary. That means it's, how do you say stationary? Stationary. 静止. Okay. So yeah. So become 静止 hydraulic jump. Okay. And this one is when your U is become very, very small to a certain point. Okay. Okay. Cannot jump over. Okay. So it's totally blocked. Cannot go over. Okay. So that go over. Okay. This one is just like when you go to the mountains or go look at the stream, okay, a creek, okay, shall see, okay, and you see a lot of rock and flow, a lot of them cannot go over, so they go around it, okay, because they don't have energy to climb it over. Okay, so this is called totally blocked flow, total blocked flow, and this is called the kind of hydraulic jump. Okay, this one is stationary. This one is stationary. This is propagating. Okay, and both have the upstream propagating jump. Okay, and this upstream propagating jump could be very interesting. Okay, because you have a jump propagate against the flow. Okay, there are not many cases you have the flow. Okay, you have the kind of flow can go against the basic flow. Okay, not many cases. Okay, and that is called, sometimes it's called the bore. Okay, so I'm done here. Okay, the supercritical flow. Okay, this is called supercritical flow when flow number is greater than 1， flow 数大于1。Okay， 那叫做 supercritical flow. Supercritical flow, how do you say supercritical flow? 超临界 flow. Okay， 超临界流，超临界流。Okay， 流 flow. Okay, flow. And that's called supercritical because this is critical, right? Equal 0 is critical. So if U square greater than GH, that means flow number is greater than 1, then that's called supercritical because this is critical state. Okay, so this is greater than 1. If U square is less than GH, that's below the critical. That's called subcritical. Okay, so we are done with those. Any questions so far? Oh, subcritical. Okay. Okay, so really, when flow is subcritical, the flow number is less than 1. The steady state effect of this is to increase the layer depth upstream. Okay, because it doesn't. Okay, so say this is a mountain. This mountain, flow is coming in, but doesn't have enough kinetic energy to climb it over. So what's going to happen? Because then the flow is going to be blocked by the mountain, so it's going to accumulate. Okay, so when you accumulate, the water surface become higher. That means you increase the potential energy to a certain point. You have enough potential energy to convert to the kinetic energy. So go over, but then dip down, go over. Okay. Because you have to convert into kinetic energy. You have to depart, part of your potential energy. Okay. flow comes in Barack mountain, cannot go over. So gradually it kind of increase the height. Okay, so have enough potential energy. And then that potential energy, try to go over, then part of it have to convert to kinetic energy. That's why potential energy becomes smaller. Okay, deep down. Okay, so let me explain one more time. So say where U kind of small, that means flow number is less than 1. So flow, so flow is going to accumulate because it's blocked by the mountain, but cannot go over, so then will increase to a certain point. You've got enough potential energy. But this potential energy will be depart into potential energy plus potential kinetic energy. Over the mountain, it will become like this, MPS shape. Over the mountain, okay. So here, because it is potential energy, part of it is going to become kinetic energy. So this part, PE over the mountain, will be decreased. Will be smaller. So this PE will become smaller than PE upstream here. So because part of it go there. So if PE over the mountain, potential energy over the mountain is smaller than upstream, what's going to happen? It's smaller, that means its surface elevation will be decreased. That's why it goes down. That's why it goes down like this. Okay, so the fluid reach maximum speed. So here will be faster. Okay, like this. Okay, so here U will be less than U. Okay, so when U like this, it will be slower. Okay, and here U like this, here will be faster. Okay, so we are done with this. Okay, and you can also solve the steady state solution like this. U prime over capital U, is equals to negative 1 over F squared, H prime over H. You can also solve that. Okay, you can also solve that 3.4.19. That shouldn't be that difficult to derive. Okay, and this equation describes the Venturi effect. Okay, also related to Bernoulli effect. Okay, what does that mean? Okay. Can somebody tell me what's Bernoulli equation effect? Bernoulli. Bernoulli. Okay, Bernoulli. Okay. Anybody knows Bernoulli? Okay, effect. Low pressure. Okay. Yeah. And okay. Lower speed flow will have higher pressure. Okay. Yeah. So. Okay. So that's what they do. Okay. Okay. Do that. Okay. No. Okay. Yeah. The pitcher the baseball. Okay. So they spin. So sometimes you feel like they go this way, but some kind of wave change go this way. Okay. And some go this way. Okay. Because spin different, they will deflect. Okay. Because of pressure. Okay. Pressure. Okay. So when you flow faster, that part will develop low pressure, and then you have pressure difference that give the ball has a pressure gradient force and then deflect it. Okay. And also sometimes they prefer to hire some left-handed Dutch-wire. Okay. Yeah. Because they spin a different. Okay. Difficult for the kind of hit. Okay. To hit it. Okay. So anyway, so that related to Bernoulli effect. And here it's called Ventura effect. Okay, they are related in a way. Okay, yeah. Because the Ventura effect is when you have h. Okay, your h is your speed increase speed, you decrease the height. Okay, you decrease the speed and then you increase the height, decrease the height. Okay, there. So that basically is based on this equation. You have pressure, you have kinetic energy, you have potential energy, and all together is constant. Okay, so if you keep height same, then pressure is proportional to speed. Okay, negative speed. Okay, and this is called Bernoulli effect. Okay, if you keep same pressure, then the height and the kinetic energy, okay, the potential energy and kinetic energy are inversely proportional, and that's what we're dealing with. That's called Venturi effect. Okay, they are related because they are governed by this equation. You're not familiar, please go home and then probably look at the book chapters or try to find it. Okay. And so in a transient flow, then we have different kind of cases happen. Okay, and then in that case, we also can define other non-dimensional parameter called non-dimensional mountain height. Okay, HM divided by capital H. Okay, capital H is an undisturbed water depth. Okay, and HM is a maximum mountain height. Okay, and this is non-dimensional. Another one is flow number. Flow number is U over GH. So here we have two. So here we have two non-dimensional parameters. Where is two? Where is two? Okay, where two? Okay, one. Okay, one is M, and other one is flow number. Okay, and then they govern different flow regimes. Okay, so B, A here, the flow number is greater than 1. Okay, so that, and then E is less than 1. So these two are supercritical, subcritical flow. And P is this one. That's, we have hydrological jump, but that jump is propagating downstream. And C, we have hydrological jump, but it becomes stationary. Okay, and then D is okay, completely black flow. Okay, because here, when you're D, that means your M is greater than 1. Okay, that means mountain is very high, and you don't have enough kinetic energy associated with the flow to go over it. Completely black, like this. Okay, so like you look at a creek, okay, a creek shall see, and you see a lot of rocks, and then flow dip down, go over, cannot go over, just go around it. Okay. Okay, so I think we are probably about done with this. Okay, so this is just real case. It happened in 1972, a very famous case, 1972, over the border. Okay, border is located to the north of Denver. Okay, about 1 hour, 45 minutes driving. Okay, so here. You're coming down, and here you go from the subdental divide, the continental divide. Okay, okay. Continental divide is the highest peak over the Rocky Mountains, and then to the west, the water is flowing to the west. Okay, to the east, the water, okay, is flowing to the east. The river, okay, is flowing Okay, river water is flowing to the east, here to the west. That's why they call continental divide. And so border is here, and this mountain here. So they have flow comes in, they develop a strong downslope wind, okay, and this wind is very strong, called severe downslope windstorm, and that can reach 60 meters per second. 60 meters per second is typhoon wind, very strong, okay. And also it go downstream, or go downslope, it's very dry. So that can also create a problem because it's very dry. So if you have kind of fire, that can set big fires. Okay. And so this is like this, okay. A kind of conceptual model is like you have upstream propagating jump, you have downstream propagating jump like this. Okay.
The upper part, the solid number, the solid line is similar temperature.
The potential temperature. Potential temperature. Yeah, potential temperature. Okay. And do you know those curves? You see those curves? Multipartial curves. Do you know what that curves? What, because this guy's son or daughter kind of sketch it, play with it. No, it's not. They are flat. Okay, path. Those are flat paths. Okay, they observed. Okay, so it's severe downslope wind. This is now you understand. Okay, so now this is a change of flow. Okay, and I'm looking to the south. Okay, this is Sierra Nevada. Okay, so flow come over from California, going and then develop hydrogen jump. Okay, and that's critical flow. Okay, for example, okay, you don't have solution for steady state. Okay, so you have downstream propagating jump. This one is probably stationary jump, coming down and jump up. Okay, this downstream jump. And sometimes you can observe the upstream propagating jump, that ball. Okay, you can observe that. One famous example is, have you heard of Qiantangjiang? Yeah, Qiantangjiang Jiangcao. Okay, that's okay. Propagate against the flow. Okay, that's okay. It's ball. Okay, that's upstream propagating wave. Okay, jump. And originally, I was trying to follow my mountain meteorology class in North Carolina. That normally we have 4 or 5 projects, but I think probably a little bit too overwhelming to you. And so what I'm going to do is, I just will probably go with the first project and see what happens. Okay, we try to do this problem. Okay, so we try to do a project which will ask you to change the parameters. Okay, and you can change the mountain height. You can change the capital H. Okay, you can change U, capital U, and then to see if you can find those different regimes. Okay. Yeah. So we are going to do a project to see if we can do that, can follow. Besides, also have the homework problems. But I kind of reduce the homework problems. Okay. Yeah. I reduce it to just minimum number. Okay, so I let you read those. Okay, yeah. So later, don't worry about this. Later, we're going to study the severe downslope wind storms when we talk about mountain waves. Okay, so this will do that. But for now, I want you to have the feeling about those different flow regimes. So try to do a simple problem, and I'm going to give you as a gift, the fortune program. So then you can look at that and then plot. Okay, and I probably need you and and you to help them. Okay, how to plot them. Okay. Running program shouldn't be a big problem. You can go into that fortune program. You can change numbers. Okay, nonlinear effects. Okay, if the nonlinear terms are kind of considerable, they cannot be ignored. Then 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 we want to understand what's the effect of the nonlinear effects. Those terms. Okay, remember when we solve the problem, we simplify the equations, but equations from the more complicated equations, which we have partial t plus u partial x. Okay, and then we have u prime. Remember that? Okay, and this. But this one is simplified from capital U plus u prime, and then and then partial u prime partial x, and this one we ignore it. Okay, that's called linearized equation or linear solution. Okay, equation. So we ignore it. If u much less than u, if this is not true, then you have to include that term. And then you have nonlinear effects. Okay, so what's are nonlinear effects? Okay, so here I sketch in my book. Okay, I sketch in 2007. I sketch it like this. So say you have a wave like this, and then now you just imagine this wave is composed by 3 blocks. Approximately by 3 blocks. Of course, you can use more blocks. You 100, just like a calculus, then become very close to the real amount. Okay, real wave. Okay, so just simply consider roughly we have 3 water blocks like this. Then, according to the shallow water theory. Okay, according to shallow water theory, let me see, I think I need a book. Okay, Dr. Lin, Parent Lin, okay, I know you give that back to him, and he said he's going to bring back to me. Huh? Yeah. Oh, under his desk, and you can open his office. Oh yeah? Oh, can you get it? Yeah. Okay. That's probably make it easier. So when so let's do this. So for this one, the depth of the flow is h1, right? Okay. So C3. Okay, we have the depth of the flow roughly like h3, and C2 would be like h2. And C1 will be H1. Okay, so here, so this is C1. So say here is H1. So C1 will be equals to what? It will be will be proportional to square root G H1. Right. Right. That's a shallow water wave speed, okay, equals to this. Okay, will be, or say will be equals to this. This is called shallow water wave speed. Okay. So, okay, this one. Okay, this one called shallow water wave speed. Okay, shallow water wave speed. So this shallow water wave speed. And now, if on top of it, you have this, and then here you have H2, then where C2 will be equals to what? Square root G H2, right? So C2 will be greater than C1, agree? Because it's deeper, okay, deeper. So, okay, that deeper fluid will give you stronger flow, okay, like this. So that means C2 will be bigger than C1, and C3 will be bigger than C2. So then, okay, so then what happened is C3 will be, oh, thank you. C3 will be larger than C2, C2 is larger than C1. So then C3 will be kind of following, okay, flowing faster. So it's going to run in, okay, gradually catch up C2. And then C2 is going to catch C1, eventually going to like this, okay, because C3 is moving faster. And C3, according to, just broadly speaking, according to the shallow water theory, C, the shallow water wave speed, is equals to square root of GH. Okay, that's called shallow water wave speed. And then, so then it's going to be overturned because it is far faster than this. Okay, so it's going to overturn it. Okay, and this is called steepening effects, and then eventually become overturning. Okay, and so now if you go to beach, okay, plain water, okay, and now you understand what's going on. Okay, that's beach wave. Okay, that's beach wave. No, it can be nonlinear. Yeah, it can be nonlinear. Yeah. Okay, we just use assuming linear, we assume steady state, and try to get simple solution to explain some basic dynamics. Okay, so when you go to the transient time-dependent flow, like the regimes on the right-hand side, they are time-dependent, they are nonlinear. Okay, without linearity, you don't have the hydraulic jump. Okay. So say if you have so say this is so say this is beach, and here is water. Okay, and this is under the, okay, and this is a land here. Okay. So here's water, right? So water, here's water. So water here, speed will be greater than here. Why? Deeper. Okay, see deeper. So your C will be equal to square root GH here. Here is C equals to square root GH here, right? So this H is smaller than this one. So this is also C2, H2, and C1, H1. Okay. But write it more clearly so people over there, they can see it. Okay, so here, okay, your C2, C1 will be equals to square root GH1. And here will be faster, C2 equals square root GH2. Okay, so you're faster. So what's going to be accumulated because you catch up here. So that's why then you develop wave. You develop wave here. And wave will return over, and that gives you the pitch wave. Okay. This reminds me, I think there's one. Okay, I guess we are almost done. Okay, we are almost done in this. Okay, so now you may wonder why I wanted to spend time explaining this, because it's important for related to our real atmosphere flow. Okay, so you look at this. Okay, this is published by a graduate student at NC State, North Carolina State University with me. Okay, and he's in Taiwan now. Okay, yeah, I don't know if you know him. Okay, he's in the Kejibu. Okay, the Wang Ting An. Okay, yeah, Kejibu. Okay, so so here, this is stratified flow, the atmosphere flow. Okay, so you can see flow. As time goes, can develop hydrographic jam. If flow is faster, then you can go over this almost like supercritical flow. Okay, you can develop like this. Okay, and this is kind of hydrographic jam here. And here is, see here, black. And those lines are potential temperature. See here? Okay, because potential temperature, if there's no heating, okay, no cooling, no friction, then flow particle will be follow the potential temperature line, right? Because theta is conserved. So your flow will come like this, and then black. This is completely black. Okay, this is hydrogen jam. Okay, stationary, and this is propagating. It's propagating because the basic flow is stronger. Okay, so you also have shallow water, mimic shallow water flow, not exactly. Okay, and when you have supercritical flow, difference is since we have great wave developed, and in the shallow water wave, okay, we don't have kind of this because we don't have stratification. We don't have density difference called stratification. Okay, 层层, okay, okay, stratification. So then you develop great waves, and we are going to talk about great waves in next chapter. Okay. Okay, so this is probably a good time to. Oh no, not wait before you go. Okay. Oh, here just show you. Okay, because we have so many models, and we don't know they produce different results. So we do model comparison. So we did one model comparison. I participated in this one too. I'm a co-author of this paper, and every model, okay, kind of behave differently. Okay, so that's why we also need observations to verify the model to see which model, okay, is more accurate. Okay, and so that's why. And you can see, okay, different model have different kind of behavior, but normally they all develop a hydrographic jump. Okay, hydrographic jump here. So now you don't understand this hydrographic jump here, severe downslope wind. You can have. Okay, so we can have the downslope, severe downslope wind, and then hydrographic jump here. Okay, so almost everyone has that. Okay, participated. Okay, I use ARPS to participate. Okay, Dr. Huang used this model, Central University mesoscale model to participate. Dr. Huang Qingyong. Okay, and this is 2011. Okay, they also do similar thing, but over the over the kind of Sierra Nevada region, they have this. Okay, also model, different model. Oh, you can see here, you don't have much going on, but here, kind of very strong, very strong. Okay, so that's why we need a field experiment observation to verify. And then let me see, let me close this. This one. Okay, so this is the homework. Okay, so you download homework, you start work on that. Okay, yeah, start work on that. Okay, so this homework number 1, you prove through point 3.1, 2.3.2, 2.3.3 are identical. Okay, I give a hint. And then second one is interesting because it's not difficult. The second one is you just based on 3.4.4, 3.4.6, you reduce, simplify the equations. Okay, and 3D you still assume 3D and linear, and 1 layer. Okay, 1 layer means you. Okay, you don't have 2 layers. Okay, so rho 1 will be equals to rho 0. Okay, so it becomes simpler. Okay, so that means G prime will be equals to what? G prime will be equals to delta rho divided by rho naught times G. Okay, and rho naught delta rho will be equals to rho naught. Let me see. I know one. It becomes rho naught minus rho 1 divided by rho naught times G. But the rho 1 is equals to 0. Okay, so it becomes G. So you just simply change G prime to G. Okay, so equation becomes simple. And then you follow what I did. Okay, so you follow I did, and then okay, try to use the normal mode approach to do to derive the dispersion relationship, and then try to decide. Also calculate phase speed, group velocity, and then try to decide, determine it is dispersive or not. If it's dispersive, if not, you also have to justify. You have to prove it. Okay, give that reason. Okay. And then number 3 is do this. Okay, and then number 4. Okay, no, number 4. And then project 1 will be doing this. Okay, I'll give you the equation. I'll give you the model, and then you change the parameters, and you plot it, and then to show the produce different regimes. Okay, different flow regimes. Okay, it's probably difficult to get this one, but at least you can get those 4. Okay. Or at least one of them, okay, and this one, and this one, and this, at least one of them. You can catch 2, would be the best. Okay. Yeah, so start to do the problem, okay. I think the homework, you can start to do it now, and then for the project, Chia Hong is going to help you to, yeah. Okay.
How about the homework is due in July 4th?
July 4th. Probably 5th. Yeah. What do you think?
No, I just asking about the visa.
Huh?
No, I say it's due on July 4th for sure, right?
Yeah. Okay. Yeah, because 1 day is equals to one week. Okay, so we're kind of very intense. Yeah, because it's short course, so it condenses into 4 weeks. Okay, so 1 day is almost 1 week. Try it. We'll see what happens. Okay, yeah, try it. Yeah. You don't try, you never know what your potential is. Okay. Any questions, especially homework and any complaints? Too much? No? You haven't tried it, so you don't know too much. Okay. We'll see what happens. Okay. We'll see what happens. This one possibility is probably you can focus on 2 and 3 because 1 probably take a little bit effort. Okay, you need a more theoretical background, but 2 shouldn't be that difficult. Okay, 2 shouldn't be difficult. Okay, and 3 you should be able to do it. Okay. Okay, yeah. Okay, give it a try. Yeah, and then we'll do this project. But one good news is originally I was planning to have 4 projects. Okay, but then we probably just do this project. That's one good news. Okay, okay. So you can start to do this. Okay, but it will have longer time. You don't have to submit by July 4th. Okay, okay. So this one will take whole period. Okay. Okay, any questions? This one? This one? Oh, down. Oh, B is this one. And C is this one. Okay. Yeah. And E is this one. And A is this one. So what you can try to do, try to find those 4 regimes. You have parameters. Okay. Your M and F. You find M here. Okay. F here. This F, right? So all these areas, the parameters, theoretically can produce, okay, this type of flow. In this area is M. If M is here, then you have to find F in this area. If your M is here, you have to find F in this area, okay, this range here. And then you can produce regime C. Okay, you know what I mean? What's your question? 你可以讲中文。
有知道为什么它会水药会有水药
？Yeah, right. 水药现象，这样。
不知道为什么。
会有这样。
会有这样子。
哦，现象。哦 ，OK. So, question is why there's a jump there? Okay, it's because when your flow comes in. Okay, let me probably show you another figure. Let me show another figure. Okay. Chapter 3, right? Chapter 3. See here, here these two are kind of critical. Okay, so you increase the height of the water upstream. So say this is a mountain. Okay, so this is a mountain. You increase. Okay, and then that will increase the potential energy like this. Okay, potential energy. But this one, okay, since it's critical. Okay, it's close to, okay, the square root GH is close to that U. Okay, so it's critical. So here you can develop a very strong downslope wind. And when it's downslope wind, rush downstream, because downstream flow is slower, so you have rush flow, and then with strong convergence and develop jump. You know what I mean? So if you have a strong downslope wind, rush down, because ahead of it, the flow is just capital U, right? Basic flow. And then that will try to push this one, but this produce strong convergence, and then strong upward motion. That's why I jump there. Okay. Because it's very strong here. Okay. Because your potential energy, okay, converted to kinetic energy very strong, and then flow here is slower, so it's going to produce a lot of convergence, and water has nowhere to go, just go up, can jump up. That's called hydro jump. Okay, so I think we should stop. Okay, and continue at 2 o'clock. Right, 2 o'clock. Yeah. Okay, so I see you guys this afternoon at 2 o'clock. Yeah. 12:10. Okay, okay. Oh, okay. Okay, yeah, thank you. So I told Dr. Lin I'm going to borrow this. Okay, yeah. Already. Okay, thanks. F 就是那个 full number， yeah F， yeah U， yeah right square GH， M is M delta H， okay yeah. So think about this. If their depth is constant, okay, then basically MC is just related to mountain height, and this is constant, right? So it will be F will proportional to U. So basically you can just roughly speaking, okay, 这边呢就是增加山的高度，这边呢是增加水的流速。Okay, yeah. So that's two control parameters if capital H is constant. Okay, so you can think that way simply. Okay, 所以你这边呢，假如说这边这样讲好了，这边假如说 mountain height constant, okay, 那就变成这样子，就 control by U. So okay, so 流速越大呢，它就变成 supercritical， 流速越小呢变成 subcritical。OK， mountain 小的时候就这样子，但是 mountain 增加的时候呢，它就有些新的那个现象出来。对，它这边的层面是不会，看河流。这个 PC 主要就是看下面就这个够不够强的差别。对，看这个是。那如果这个太强的话，就会直接跳上来。这个就是它强，而且它这个会流动，因为它的 U 呢比较大，它这边 U 比较大。OK， 这边是 U 比较大 ，U 嘛哈，这边 U 比这边小，这边小的时候它变成 stationary， 它会形成，但是呢不会流动，这个 jump 会停在那边。所以这边是 stationary。呀，对，这个是 stationary。那这边没有。这个会动。呀，因为它的那个，它这边 U 比较大嘛哈。这边 U 比较小，对 ，F 比较小，就是 U 比较小，这 U 比较大，U 比较大呢，它这个会把它带到下游去。 又到的时候带到下游去。